Take a number like 123,456,789. At this scale, the digits appear almost random. But integers aren't just arbitrary symbols. They are built from a rigid internal structure. We interact with this architecture daily when we calculate distances or manage finances, yet we rarely consider the underlying rules, the mathematical source code, that dictate how these numbers must behave. The search for these indivisible building blocks began with ancient geometry, but the formal proof of this structure didn't arrive until 1801, when Carl Friedrich Gauss published his work on the properties of integers. Gauss formalized the fundamental theorem of arithmetic. While it specifically describes the behavior of positive integers, it provides the logical base we need to prove the existence of numbers that cannot be expressed as simple integers at all, the irrationals. The theorem states that every composite number can be expressed as a product of primes in exactly one unique way. Let's deconstruct 32,760 using a factor tree, dividing by primes repeatedly until we reach the indivisible components. This yields a specific sequence: 2 cubed times 3 squared times 5, 7, and 13. The order might change, but the ingredients never will. This sequence acts as a mathematical fingerprint. Because the theorem guarantees this factorization is unique, we can use these prime ingredients to determine the properties of a number before we even perform a calculation. Consider a predictive problem. Will the expression 4 to the power of n, where n is any natural number, ever result in a value that ends with the digit 0? To end in 0, a number must be divisible by 10. Its prime factorization must contain both a 2 and a 5. If we look at the base number 4, we find only 2's. There is no 5 present in its architecture. Because the fundamental theorem of arithmetic guarantees that the prime factors of 4 are unique, no amount of multiplication will ever introduce a 5 into the sequence. We have reached a definitive conclusion without calculating a single exponent. No power of 4 will ever end in 0. We can also use these prime ingredients to map the specific relationships between different numbers, such as 6 and 20. We find the highest common factor by taking the smallest power of the primes they share. To find the lowest common multiple, we take the greatest power of every prime involved in both numbers. This reveals an elegant symmetry. The product of two numbers is always exactly equal to the product of their HCF and their LCM. This logic leads to a secondary rule, Theorem 1.2. If a prime number divides a square, a squared, it must also divide the base root, a. By understanding these prime relationships, we have the evidence needed to investigate the nature of the square root of 2. To prove the square root of 2 is irrational, we begin by assuming the opposite. We assume that the square root of 2 can be written as a simplified fraction a over b, where a and b share no common prime factors. If this assumption is correct, the logic of our prime rules must remain consistent. If we find a contradiction, the fraction itself cannot exist. First, we square both sides and rearrange the terms to get 2b squared equals a squared. This tells us that a squared is divisible by 2. If a squared is divisible by 2, then a is also divisible by 2. We can rewrite a as 2c. Substituting this into our equation gives us 2b squared equals 4c squared, which simplifies to b squared equals 2c squared. This proves that b is also divisible by 2. This is the contradiction. We proved that a and b share a common factor of 2, which is impossible if the fraction was already simplified. The fraction a over b cannot exist. Since the rational fraction leads to a logical impossibility, we must conclude that the square root of 2 is irrational. This same reasoning demonstrates why the square root of 3, or more complex values like 5 minus the square root of 3, are also irrational. These prime sequences provide the immutable blueprint for everything else in mathematics. By identifying the indivisible building blocks of integers, we gain the logical tools to navigate the infinite complexity of the real number system.